Hello, everyone. Thank you for the introduction. Today I'm going to talk about a topics about decoding of topological quantum codes. So in a quantum computer, we usually have very noisy quantum states, noisy quantum operations. So to protect this quantum, 等一下，我把这个关掉。Sorry. Okay. So my research areas is about quantum computation, and most of my recent work is about how to build a quantum computer. Okay, how to build a quantum computer. Currently, we will have noisy quantum operations, noisy quantum qubits. So in this situation, we want to protect the quantum states so that after we perform some noisy quantum operations, we still have some chance to obtain the result we desired. Okay, so we will use the techniques of quantum error correcting codes. So these quantum error correcting codes are similar to classical error correcting codes. Okay, so for example, in communication, in your cell phone communication, your information will be protected by error codes. And using this wireless communication, you can send information from one sender to some receiver. Okay. So that's the so we want to apply this quantum codes. So a quantum state will be protected by some mathematical structure, such that if some errors occurs, we will be able to detect the errors and maybe do some recovery. Okay, that's the basic idea. And currently, the most important family of quantum codes is topological codes, meaning that we will have a two-dimensional layout, and we will put QP on this layout. For example, the figure here, these figures are called color codes. Okay, color codes. Here, a square grid here with a number. Okay, here, each number denotes a QB. Okay, and each grid with a color denote something called parity check. Okay, so this is some illustrations. So today I'm going to talk about how to perform error correction on this kind of lattice. Okay. If you have any questions, please raise your hand. Because I'm from electrical engineering. I think most of the audience here are from physics. So today I'm going to talk about more about computation or information processing. Basically, there will not much physics involved. Okay. So if you have any questions, please raise your hand. Yeah. Okay. So 这个 delay 有点严重。Okay. Today I'm going to talk about my recent work with Dr. Gao Yue Guo. Okay. Gao Yue is also a postdoc in our institute. Okay. So in this talk, I will focus on this paper, the second one. The delay is too much. Okay. So basically, recently we developed some decoding scheme for sparse quantum codes. So we would like to apply these decoding schemes for these topological codes. Okay. And I will tell you that this is a very important problem in quantum occurring codes. Okay. you want to protect the quantum information. So you have to encode the information, and then you have to perform error correction constantly because errors will accumulate over time, right? So you have to do error correction constantly. And because the quantum operation need to be done very fast, right? So you need to have a very efficient decoding algorithm. Okay, you want to decode very quick in maybe in microseconds, something like this. Okay, so we want to have a very efficient decoder. So in classical communication, a very famous decoding algorithm is called belief propagation. Okay, here, belief propagation. Belief propagation. But this algorithm does not work for this quantum topological code. Okay, so we would like to improve this situation. Okay, so this is like an open problem for more than 15 years. Okay, so we have a series of work in these 2 years, and I will going to tell you how do we improve this. So this is Google's quantum chip called CQSE, right? I think it's from maybe 2 years ago. They have this qubit layout, right? You have seen this, right? Each cross here denotes a qubit. Okay, and they have like a 53 qubit here, and a qubit has some. You can do some coupling from a qubit to its neighboring qubit. Okay, but there's no long-term interactions between any two qubits. Okay, you only have some local coupling here. And from the data they provided here, there are some single qubit operations, two qubit operations, and some measurement operations, right? So these are their error rates. Okay, so you can see these numbers, they are around 10 to the minus 2 to 10 to the minus 3, right? These numbers here, right? Numbers here, they are from 10 to the minus 2 to 10 to the minus 3, okay? So there are many other physical architectures to implement the quantum computers. Usually they will have numbers like this one. For some schemes, they may have better single qubit gate or may have better two qubit gate or better memory, better quantum memory. But usually the numbers for those other schemes, they will be like this one. So the error rate, the physical error rate is usually about 10 to the minus 2 to 10 to the minus 3. Okay, remember this one. So previously, Google have demonstrated some so-called quantum supremacy using the quantum computer to implement some specific quantum task. You can say this is some sampling problem. Okay, you know this one, or probably you have seen this. Are you familiar with this one? I'm not sure. Do you want to talk? Do you want to know this? Maybe I can say more. So, in Google's quantum computer experiments, they have 15 3 qubits, right? So in this quantum circuit here, in this quantum circuit, okay, this is a quantum circuit, and each line denotes a quantum qubit, right? So they are in this plot there are 5 qubits, okay, and each box here is a single qubit gate, and this thing here is a 2 qubit gate, okay. So they will randomly choose a single qubit gate for each qubit and some 2 qubit gates between each stages of single qubit gates. Okay, so this is a stage, and they can perform like 20 stages here. Okay, they will have 20 stages here, and then they will perform a measurement at the end. Okay, so this is a quantum experiment. So you do a measurement, you get a distribution, right? And because this circuit is random, this is a random circuit. So mathematically, you know the answer of this distribution, but you cannot compute the distribution efficiently if the number of qubits is too much, large enough. Okay, if there are large enough qubits and the circuit depths are long enough, you cannot compute this distribution by a classical computer. That's what they want to say. Okay, you see my point? Anyway, so there's another story. So when Google claimed their results that using this quantum chip, they can produce like 10 to the 6 a million samples in 200 seconds. So classically, he said if you want to do this sampling, you need like 10,000 years using IBM's supercomputer. But IBM later claimed that you only need 2.5 days to do this task. However, there is still a very big gap between 200 seconds and 2.5 days, right? So there is still a huge gap between these two numbers. So we still believe this is something called quantum supremacy, meaning that we can use a quantum computer to perform some tasks that that cannot be efficiently done in a classical computer. Okay. One million times. Yeah. Okay. And later, let me skip it sampling ideas here. So later you see this one, a quantum computer from China called Jiuzhang. So this is a photonic quantum experiment. Okay. They build up these photonic circuits and then perform some tasks very similar to the sampling experiments. So it's like this one, if you have beam splitters, you have a beam splitter, and you have a photon coming to the beam splitter, it will go through the beam splitter, or it will be reflected, something like this. So it's very similar to this pinball table. If you have a pin here, and when the ball hits the pin, it will go left or go right. And if you play this game several times, you will get like a Gaussian distribution of the outcomes, right? So similarly, they do this photonics experiment, and they get some kind of distribution. Okay, and they claim that you cannot simulate the distribution using a classical computer. Okay, so the result is very similar to Google's experiment. Okay. Anyway, but this title is misleading, so let's forget this title. 这个标题是骗人的，不要相信。Okay, so in our task, in our task, we want to finish a real computing task. Usually we'll talk about this experiment called integer factoring. Okay, here the task is to find a non-trivial integer factor of a composite number. Okay, suppose we want to do this factoring number with L bits. So the size of this composite number is roughly like 2 to the L. Okay. So currently, there is no non-classical algorithm can do this factoring in polynomial time in this form. Okay. For example, from the classical, from the elementary textbook, you know that you can do some like if you want to find a factor of n, you can check the prime numbers from 2, 3, 5 up to square root of n, right? Something like this. So this will give you a square 2 to the L test, right? Something like this, and take a square root. So this is 1.4 to the L. So this algorithm is exponential. Okay. However, there's no polynomial time algorithm in classical algorithms. Currently, the largest number that can be factored is this RSA 768. So RSA 678 is a crypto system. Okay. The security of this crypto system is based on the assumption that factoring is difficult. Okay. So to factor this number is like it has 768 bits. So it's roughly 200 decimal digits. Okay. So if we want to do the factoring of these numbers, you need like 10 to the 20 operations, which takes roughly 2,000 years, right? Because usually the classical computer will operate at a CPU around gigahertz. So gigahertz is 10 to the 9 operations per second. So you need like 10 to the 10 seconds. So that's too long. Okay. So in Peter Shell's quantum algorithms, it takes time L33. Okay, L33 with L qubits. So here, L is like 1,000, right? We have 1,000 bits. So we need 1,000 qubits. And the time will be 10 to the 9 or roughly 10 to the 10, right? So we need 10 to the 10 operations. So compared to the classical algorithms, which is 10 to the 20, we have an improvement of 10 to the 10, right? Here L is 1,000. So L33 is roughly 10 to the 10. Okay, so 10 to the 10 compared to this number of classical algorithms, we have some improvement, right? So if we have a quantum computer with 1,000 qubits, and if the quantum CPU is around gigahertz, this factoring can be done in like 10 seconds, right? So this is a very impressive result. Okay, so we need a quantum computer with like 1,000 qubits that can afford 10 to the 10 operations. So far, so good. Okay, so there are many other examples, maybe in chemistry simulations, or you will need roughly this number of qubits and roughly this number of operations. Okay, in a quantum chemistry experiments, they say that you can have some benefits if you have a quantum computer with like 300 qubits. Okay, so they have a similar result. Okay. However, currently, I just said the quantum operation is noisy, right? And the error rate is around 10 to the minus 2 to 10 to the minus 3. So if we want to implement this kind of operations, you need the error rate to around 10 to the minus 10, right? Such that you have some non-trivial probability to success, right? you need to perform this much amount of operations. Okay. So you need quantum operations to be accurate up to 10 to the minus 10. Okay. However, it is very difficult to achieve these numbers physically, right? You can have an improvement of 1 order or 2 order. That's already very impressive. However, there are 7 orders here. Okay, so this is a very important target. Okay, so we would like to introduce the idea of error correction. Okay, let me skip this part. So let me give you some feelings about error correction codes. Okay, let's quickly review these ideas. So basically, the data will be handled digitalized. So they are binary digits, right? So like this one, 0 and 1. And in a communication channel, we will model this binary bit flip channel so that when we send a bit 1 or a bit 0, it will be flipped with a probability P. Okay, this is called the physical error rate P. Okay. So error correcting codes are an idea to protect digital information from noise by adding redundancy. Okay, the idea is like this. Suppose we have a very big space for our data. Okay, so suppose this in a small space we have this data points. So we will encode this small data set into a larger space. Okay, so in this larger space, I choose this blue point to represent the original data. Okay, so basically, so in this raw data space, if there are some error occurs, the data will be corrupt. So it will become some other data points. So you cannot recover that. In this case, if there are some error occurs, for example, this group point will go to its neighboring node, right? So when the error rate is not too much, when you see this yellow point, you will feel that it is from this blue one. It cannot be from this one, right? Because this is too far, and this is very close to this one. Okay. So if we assume the error rate occurs independently on each bit, so we'll have this kind of distribution. And when an error with high weight, it will occur with lower probability. So we would like to handle the most likely errors, meaning that we want to handle low weight errors, okay? The most likely error. So maybe let's consider this simple example. So this is the basic example of an error correcting code. Here we have, this is called a repetition code. So here we will encode a bit 0 into 0, 0, 0, and encode 1 into 1, 1, 1. Okay. We use 3 bits to represent a data point. Okay. So this is the illustration of the space. So this is 0, 0, 0, this is 1, 1, 1. So if you have a bit flip error occurs, 0, 0 will become 1, 0, 0 or 1, 0, 1, 0 or 0, 0, 1, right? If there are 2 bit errors, 0, 0, 0, 0 will become 1, 1, 0, 1, 0, 1, 0, 1, 1. Okay, so if But usually single bit error is more likely than 2-bit error. So when you see these 3 points, you will determine that it is 0. And when you see these 4 points, you will say this is 1. Okay, this is the basic decoding rule. So what is the error right now? After this decoding, we will have a logical error if there are 2-bit flips or 3-bit flips, right? So if there are 2-bit flips, the 000 will become 110, and you will say this is 1. So you made a logical error. Okay. The probability of 2-bit flip error is 3 times p squared. Okay. But original, the physical error is like p, but it goes from p to 3p squared. So from p to p squared. So logically, the logical error can be decreased using this airplane code. Okay, that's the idea of airplane code. So you can imagine that if we increase the size of the code, for example, if I use 10 bits to represent 0 or 1, then the error rate can be much better. Okay, and a very important problem is to do the decoding. Okay, here we have a parity check matrix H here, 110, 011. Okay, the meaning is that a code word should be in a null space of H. Okay, so meaning that if C is a code word, HC is equal to 0. Okay, for example, here I have 2 logical code words, 000 and 111. So using the first law here, I will call a parity check. It will check the parity of the first 2 bits. And the second code will check the last 2 bits of the parity, right? So when you see some error, using this parity check matrix, you will have some syndrome bits, and you make a list of errors corresponding to this syndrome, and you pick the most likely error. You will say, oh, this is the error. Okay, this is called a lookup table decoding. However, if you have too many parity checks, the size of this table is like exponential in the number of checks, right? The number of, suppose I have R bits, R syndrome bits. The size of this table is 2 to the R, right? So it's exponential. So we in practical implementation, we cannot use this kind of table decoding. We want a linear decoding, meaning that we can, given a syndrome, given an error syndrome, I can locate the error in polynomial time. That's my idea. Okay, so we would like to develop the idea of coding algorithm. Okay, I will give this part. So in a quantum case, we will have these poly matrices as a basis for linear operators on a single qubit operator. Okay. So this poly matrix I, X, Z, Y. The operations of X is like a B flip. It will map 0 qubit to 1 qubit, right? It will flip 0 and 1. And the phase flip operator Z will create a phase -1 when the input is in state 1. Okay, this is X and Z, and Y is a combination of X and Z. Okay, so usually we'll assume a depolarizing channel with a parameter epsilon such that a qubit has no error with probability 1 minus epsilon, and an X, Y, or Z error with probability epsilon over 3. Okay, this is because you can imagine that an error process is a unitary operator, and you can do a decomposition of the operator to these poly bases. Okay, and there's a theory called error quantization. You can perform some measurements in these bases, and the unitary errors will be decomposed into these linear combinations of errors. And when you do the measurement, there is only one poly errors will be left. Okay, so we only handle these discretized errors. Okay, so we can define quantum codes like classical codes. Okay, usually we'll consider these n-fold poly operators, and we define a class of quantum codes called stabilizer codes. Okay, so you know these poly operators will have eigenvalues +1 or -1. Okay, and they either commute or anti-commute with each other. Okay, they commute or anti-commute. This is the basic idea of airplane code. They are commute or anti-commute. So in the quantum coding theory, we will choose an abelian subgroup of the n-fold poly operators and their abelian. So we have these generators S1 through Sm, they are commute with each other, and we require that minus identity does not belong to this group. Okay, so this group will be called a stabilizer group. And a quantum code C of S, defined by this stabilizer group S, is defined as the joint +1 eigenspace of this stabilizer group. Okay, so if this quantum state belongs to the core, it means that it is a +1 eigenvector of a stabilizer. Okay, S is an element of the stabilizer group, and the eigenvalue of this core should be +1 for all S. Okay, so sorry. Okay, so when an error occurs, it will collapse the quantum state by E operating on Psi, right? So when you do the measurement of these stabilizers, if the error anti-commutes with the stabilizer, you will get a minus side of measurement outcome. Okay, you will get -1. So you do a measurement of the generators of this stabilizer, you will see some patterns. If there is no errors, the outcome should be all +1. If there are some -1 outcomes, then you can identify there are some errors occurred, right? Because my code space are all +1 outcome space. Okay, so when there are measurement outcomes that are -1, you will understand that some error occurred. So our goal is to recover the error from a measurement outcome. Okay, we want to identify what error occurred. Okay, according to the syndrome. So the measurement outcome are +1 and -1, so they are binary. They are binary. However, the error set we consider here are poly errors. Sorry, the poly errors. There are 4 elements, right? So they are like a quaternary code in classical coding theory, but they have binary error syndrome. Okay, so this is an example. This is an example. Here I have a classical binary parity check matrix H, and I define the X stabilizers according to the patterns of 1 in this matrix here. And I define another 3 Z stabilizers okay, according to these patterns. And then I have logical 0 and logical 1, which are +1 eigenvectors of these 6 operators. Okay, so this is a simple example of a quantum step-by-step code. Okay, so here the decoding problem is like this. We have a parity check matrix H. We use this one to define a quantum code, and we are given a binary syndrome Z. And the decoding algorithm need to find an error vector E such that E fit the measurement outcome. Okay, and E hat minus E belongs to the step-by-step group with probability as high as possible. Okay, that's our test. So a desired quantum code has this feature. First, feasible syndrome measurement. Okay, because we want to do error correction, we need to do the syndrome measurement first, and then we do a decoding algorithm to find the error. Then we perform the recovery operator. So this syndrome measurement will be performed constantly. So they need to be feasible, meaning that only a small subset of the qubits are involved in the syndrome measurement. Okay, and the involved qubits should be close to each other. So we have this locality constraint, and there is also a sparsity constraint. Okay. So classically, the most important family of codes are these LDBZ code. They are low density parity check code. For this code, they have a sparse syndrome measurement. They have sparse syndrome measurement. And there's a very good algorithm called propagation BP. Okay. So currently, the most important quantum code is this one, the surface code. Okay. So here, a white circle is a qubit. A white circle is a qubit. And a green cross is a Z parity check. And the yellow cross is a X parity check. Okay. So you can see this layout is the blueprint for Google and IBM's quantum computer, right? We have the layout here. This one, this is a service code. Okay, so they are using service code. So this is the performance analysis of the service code. Assume there is only X error here. Okay, so D is the size of the side of the lattice. So when you increase the size of D, you will increase the airplane ability, and you see the X axis here is the physical error rate. The Y axis here is the logical error rate. So you need to you expect that the logical error rate should be lower than the physical error rate. That's our goal here. So you need for example here, the blue line here is D equal to 3. When you increase D to 5, the performance is this green dotted one. You see the logical error is lower than the blue one. Okay, so when you increase the performance will be better in this direction, right? And you can see this in this simulation, there is a threshold here, meaning that when the physical error rate is below this number, you can increase the size of D so that you can decrease the logical error rate as much as you want. Okay, so this is a threshold here. the number is roughly like 5 times 10 to the minus 10. Sorry, 5 times 10 to the minus 3. Okay. So you can see that our experiments have physical gates with fidelity around this ratio, right? But if we want to perform a real quantum computation, we need to have gates below this ratio with 1 or 2 orders. Okay. So assume that we have a physical error rate in 10 to the minus 3, and we want to have a logical error rate of 10 to the minus 10. So you can imagine if you do an auto, okay, 10 to the minus 10 is roughly here, right? Something like this. So it tells you that you roughly will have D equals to in this area, right? So it tells you that you need like 1,000 physical qubits to encode a logical qubit. Okay, you need a lattice like this one with side length around 35. So the total number of qubits would be like 1,000. Okay, to encode only a single logical qubit. And in this decoding algorithm, the decoding algorithm for this service call is a minimum weight perfect matching algorithm. This algorithm has complexity around D to the 4 times log D, D to the 4. So this is a polynomial time algorithm, but this is not a linear time algorithm. Okay, this is D to the 4. So in practical, we want a decoder with complexity as low as possible. Okay, so a good candidate would be this Phys propagation. Phys propagation has complexity around D squared log D, D squared log D. So it will be better than perfect matching. And due to the time limit, I will skip the introduction of BP. Okay. Let me give me a flavor of Phys propagation. It's a kind of message passing algorithm. You will try to pass your message to your neighbors. Okay. So here we have some people. Okay. And if you can talk to the people in your neighborhood, then there's a line connecting these two people. Okay. So the task here is to ask you how many people in this plot. Okay. So the idea is that you tell your neighbor how many people are around you. Okay. So the rule is that if you have n neighbors and you collect message from n-1 neighbors, then you will tell the last person the n-1 information. Okay. Following this rule, you will see at the end they will know all the answers. Okay. So in the first round, these green people will tell the neighbor there's only one person here. Okay, they will tell the neighbor. So in the second round, the blue people will tell the remaining person there are two people and him here. So he knows this guy here knows there are three people, something like this. So continue this process, you will when it ends, everyone will know how many people in this group. Okay, this is the idea. And this is called message passing. So let's back to Yes, the message will go through of every node. So everyone in the group will know the answer. Okay, so when the maybe so when the yellow one heard the information from these two, these three, he also get the information from the green one, so he will tell this one the information. And in the next slide, this orange one will get information from here. So this one will tell information back to the yellow one. And when yellow one can have the information of the orange and the blue, he will tell the green one these informations. This is the idea. Okay. So we want to apply this idea in the decoding. Okay, so here, this is the classical parity check matrix H, right? 110, 111. Okay. So here we define a vector graph according to this parity check matrix. Okay. Here we have three variable node and two parity check, right? So we have three variable node here and two parity check here. Okay. And they are connected according to these matrices. Okay. So the parity check 2 will check the relation between 1, 2, 3. 1, 2, 3. The parity check 1 will check the relation of bits 1 and 2. So this is 1, 1, 0. Okay. And we also have some channel information. We know that the bit flip error rate of each bit. So they are here, the bit flip error rate, 0 or 1. And we have some syndrome measurement outcome, right? So we have syndrome bit S1, S2. So these syndrome bits are connected to this syndrome, also the parity check. Okay, so we have this vectoring graph. The goal here is to approximate the maximum likelihood decoding probability. Okay, so we want to maximize the probability that when you solve the syndrome Z, we get when you get the syndrome Z, we want to maximize the probability that bit xj is sent. Okay, we want to maximize this probability. Okay, so the idea is that like the message passing algorithm. Okay, so here consider this red line here. So you know the outcome S1 here. So syndrome variable node 1 will tell parity check 1 that this bit is more likely a 0 or 1 according to this value. And according to the message from this node and this bit, this measurement bit, check node 1 will tell variable 2 that you should be more like 0 or 1, something like this. Okay, because they have to verify, they have to satisfy this relation. When x1 is more likely to be 1, then x2 should be more likely to be the class of x1 in x1. Okay, so there will be message recursively updated in this graph. We will send the message from check a node to variable node, and also from variable node to check a node. And if this graph is a tree, you will get the optimal solution at the end. Okay, if the algorithm, if the graph is a tree, this message will converge to an optimal solution. Okay. However, if there are some cycles in the message, if there are some cycles in the graph, you see the message will be passed through these cycles, right? So in classical coding theory, we will try to use codes with long cycles. If there are many short cycles, for example, cycles of length 4, like this one, this cycle has length 4. So the message will be passed always in these 4 cycles. So if there are some unreliable messages, it will be always inside this circle. So you cannot get good results. Okay, so you want to avoid these 4 cycles. However, in a quantum code, we usually have many short cycles. Okay, like this one. We always have many 4 cycles because we want a quantum code. The quantum code is defined by a stabilizer group. The stabilizer group is composed of a billion stabilizer generators because X and Z are anti-commute. So if they commute with each other, then it implies that we must have many 4 cycles in the factoring graph. Okay, so these many 4 cycles will deteriorate the performance of Berry propagation. Right, so this is a very important question in quantum Berry propagation. Okay, so if we naively apply this algorithm to the service code, you will see this is the performance curve. Ideally, we want the performance to have this waterfall-like curve, right? But in the right side, if you apply the BP, you see if you increase the distance from d equal to 5, the performance is even worse than the short distance code, right? The performance is terrible. So we want to improve this situation. Okay. So we try to get a new interpretation of this decoding algorithm as an energy minimization problem. Okay. So we define an energy function like this one here with some parameters defined here. Anyway, the idea is that we define this energy function and we do what I say is you do a differentiation on the energy function. Okay, so classically this Berry propagation can be considered as a gradient descent algorithm. Okay, gradient descent. If you have an energy profile like this one, you can find the local minima by doing a gradient descent, right? So if you perform this gradient descent on the energy we defined here, you will get a new algorithm, like this one here. So we compare, there are some parameters, and this is the direction of a message, and this is the size of the message. Okay, so you can assume that you can think this is a step size, and this is the direction of the gradient descent. And you do this after you do this gradient descent, you compare to the original Berry propagation, you see that there is some connection between these two algorithms, and we can imagine that this gradient descent algorithm gives additional terms in the step update here. But the idea of Berry propagation will give you a similar direction to this one, but this direction is more accurate. Okay. Anyway, so the next idea here is using this energy topograph. Okay, so in a classical coding problem, we will have a energy topograph like this one. Okay, so if the error is this circle here, you will locate this local minima easily. But in the quantum case, due to the result of the 4 cycles, you will see there are several ripples here. So if you do a energy minimization, you will get trapped in these ripples easily. Okay, so you need to jump out of these ripples. So you want to increase the size of the step in the update. Okay, in the iterative algorithm. Okay. So we want to choose large step size. So on the contrary, in classical theory, if the step size is too large, the algorithm may not be converged. So usually they will choose a small step. However, here we want to large step because we don't want to be trapped in the ripples. But if the step sizes are large, you have problems in the convergence, right? So here we introduce another idea called the memory effect. We do the mathematical analysis of the algorithms, and we do there is a very subtle things in the algorithm. We can show that our algorithm has some memory, okay, or you can call it a momentum, something like that. So this algorithm has some memory effects. So this memory helps you to converge. Okay. I don't have time to explain the details, but our algorithm called MVP will converge is significantly better than the conventional BP. Okay. So this is our new algorithm. We have these 2 additional terms. Okay. So let me show you the final results. This is the service code I just mentioned. Okay, so I tell you that naively apply the BP, you get this performance. But if you use our new algorithms, you get this performance curve like this one here. Okay, so we can say that this performance is much better than the perfect matching algorithms. Okay, if you assume that you can have a perfect syndrome. Okay, so we have improved the performance from these curves to here. Okay. So this is a review article in 2021. They summarize the progress of Berry propagation algorithms. Okay, here in 2020 is our paper, this one. And after that, we have 2 improvements. The first one is called log domain coding, and the second one is the exploiting degeneracy. So the main result I mentioned is in this paper. Okay. So we can apply our algorithm to this color codes or this so-called XZZS code. Okay. These codes are very similar to the service code or the toric codes. However, we have some twisted boundary. Okay. So 1, 2, 3, 3. So we have 1, 2, 3, 4, 5. So in a toric code, you have the rounded boundary, right? So in a toric code, the 2 will be connected to 1. But here, we need to be connected to 3, which is here. So you kind of twisted the torus. Okay. These different topological codes have some specific benefits. So in this color code, it had higher code rate, meaning that you can use fewer qubits to encode more information qubits. And for this XDDS codes, they have better performance when the noisy error rate are not symmetric. Okay, for example, if the Z error rate is higher, X error rate is lower, then you may use this XDDS code. Okay, and then we do a comparison of these codes. Okay, in our recent paper here, we make a list of these codes, compare the parameters, and then we use our algorithm to do the coding, and we find some threshold here. And you can see in the first column here, the thresholds are from minimum weight perfect matching algorithm, and the second column here is from our algorithm, MBP4. And we compare this code service code toric color code. This color code is the 666 color code because this code has more symmetries in the structures, so it will have higher threshold. Okay, you can see our numbers are better than the perfect matching algorithms. Okay. In this figure, I said that there's a number here. As long as every single physical gate has error rate below this number, I can increase the size of code so that the logical error rate can be decreased arbitrarily low. Okay, so this is the threshold. So you will see that people will like to increase the threshold of a family, and physically people would like to have gate error rate to below this threshold. Okay. Right. Sorry. The number here they are different. Here we have assumption here that the syndrome measurement are perfect. So that's an ideal case. Syndrome measurement is perfect. Okay. So in this case, we have better performance than the MWPN algorithms. Okay. So next, right. We don't talk about the logical implementation. Okay. So if you consider circuit level noise, okay, the decoding will be like this one. You will also have a time domain. You have to do a measurement several times, and you will do a decoding with these 3D graphs. Okay. So currently we are working on this one. We have some preliminary results, and we probably will finish the work in 1 or 2 months. Yeah. So I will stop here. Any question? Thank you. Uh, it can handle every errors. Yeah, because we have to do measurement first. So we can have the error syndrome, right? Yeah. So in our simulation, we assume there's no measurement error, and also there's no gate error. Okay, so we do a pure theoretical analysis of the decoder first. Our next step will be this one. But the perfect matching algorithm has simulations for these models. Okay, they have detailed simulation. So they have the threshold for the circuit level noise around 0.5%. Yeah. Okay, but I can tell you in this simulation, Austin Fowler has this is from Austin Fowler's paper. He made some assumptions that ignore the Z errors and maybe some correlations in the circuit. Okay, so they have these problems, but you can imagine that the actual threshold should be lower than this one. Okay. No. Let's assume every place, every gate, every element in the circuit will have an error rate. Okay, so yes. So that's called circuit level noise. My friend also performed a decoder called a neural network decoder, and he can also analyze this circuit level noise, and he can roughly has the threshold around 0.2%. Yeah. So I think this would be a more accurate number. Yeah. 0.2%. Yeah. Yes. Yeah. Right. So when you increase the size, meaning that we use more qubits to protect one qubit. Yeah. Yes. This one? This one? This one? Yeah. Mm-hmm. So if there is no error, in the first step, you already fit the syndrome. Okay, so the algorithm will stop directly. Yes. Yeah. So the idea of this momentum and this large stable size are very similar to the case of machine learning. Okay, so actually we first have the result and then we try to get this physical interpretation. Yeah. Mhm. I'm not sure I understand your question. you want to use airplane code to protect quantum gate? It can be applied to any code. I just focus on topological codes because for non-topological code, you because in these topological codes, the degeneracy is higher, high degeneracy. They are high degenerate code, so we'll have these problems. We'll have these problems. Okay, so if the code is non-degenerate, you don't need to use our algorithm. Okay, you can already have very good performance using the conventional Fourier propagation. Okay. Any other question? So the cervical simply assumes that you need a local measurement, right? So if you have an arbitrary structure, if you can label your qubits like these service codes and perform any local operations accordingly, then you can use this service code. But if your physical architecture is not like a service, you probably can have more different design on it. So if you have a three-dimensional physical layout, assume you have a three-dimensional layout, and you can implement any three-dimensional operations as you wish, then you can have better code than the service code. Because of this two-dimensional constraint, there are some sacrifice in decoding performance or the code rate. Yeah, things like this. Okay. Thank you.